this doesn't work because this has the units wrong, because this has the units of frequency, has units of hertz, period has units of time.
There's a double factor.
And this is true, but we can do better with that. We can actually erase this tree. Because it's a sine squared. We have a sine function. So this is going to be 2 pi over omega, right? Because when t goes from 0 to 2 pi divided by omega, this whole argument goes from 0 to 2 pi. So this is 2 pi over omega. So this is pi over omega. So this whole thing is sine omega t. Now, if you have sine squared omega t, well, sine squared means you have to square this function. So when you square this function, what you get is you get something like that. And you see this function has a period of, I draw this nicely here, has a period of pi divided by omega. Not 2 pi over omega. So sine has a period of 2 pi over omega, like sine squared. You look extremely puzzled. No? Or just, appearance is deceptive.
Oh no, don't worry about it.
Okay. Okay. So what I'm going to plot on this graph here is I'm going to plot these probabilities as a function of time. And I know both of them are periodic functions of time with period pi over omega. And, well, let's see what happens. So let me take, so what happens here? So what happens actually depends. What happens depends on the ratio of these two terms. And you have different plots depending on what this is. So if your gamma is very, very small, if your gamma is very, very small, so remember what gamma is. Gamma just basically tells you the magnitude of your energy non-conservation here. So the gamma is very, very small. This means this coefficient is actually going to be small. And if you were to look at these probabilities as a function of time, so this C2 here is going to be, well, it's going to be some kind of small function here. Pretty little function of time. And your C1 is going to be 1 minus that. Now, when I say my gamma is small, it's not really a well-posed statement because gamma carries dimension here, and when it is small, this means it's going to be small compared to something because gamma has units of energy. Right? It's part of my Hamiltonian here. So energy cannot be just small. Energy has to be small compared to something. So this is when gamma is much smaller than right, so when you increase your gamma, because gamma, remember, gamma is basically the strength of your electric field. So that this is the interpretation of gamma to have in mind. So gamma is proportional to the strength of your electric field. It tells you the amount of energy non-conservation. And when you increase gamma, then of course you increase the amplitude of these terms, and now you can have then you have much stronger energy non-conservation here of some sort. Again, so these are probabilities as a function of time. So as you start in this state, in the first state, at time 0, so at a later time, you have some probability to make a transition to a different state. Because the probability to stay in the same state is no longer 1. It's less than 1. So you will make a transition to this state. Now, if you look at the physical interpretation of what happens here, then see something is happening here. So what happens here is different from what happens here. You see your E2 is greater than E1. So you start in a state with a lower energy. You start in the first state, in the low energy state. And at a later time, you have some probability to make a transition to a higher energy state. So what happens during this time is that during this time, your system absorbs energy from the external source. Because remember, energy is not conserved here. So your system absorbs energy. And over here, it can make transitions from your lower energy state to the higher energy state. Absorption of energy happens here. Now, on the other hand, what happens here is the opposite, because here you start in the high energy state, and then you have some non-zero probability to be in the lower energy state. Okay, so what happens during this time period is that the system emits energy or releases energy into the external energy sink, again, which is provided by this electromagnetic wave or whatever is responsible for this off-diagonal pieces of the Hamiltonian. So this is absorption.